which is the number of vectors in a basis. I gotta spotlight that just a second. And then I have to refocus. There we go. Okay, we're going to start with a theorem. Hey, Jared, could you mute your mic for me, please? Or actually, I can do it, I guess. There we go. Okay, there's our first theorem.
Is that any basis of V?
Yes. Okay, we aren't actually going to prove this, but I want to give you an example so you see what happens in each case. So let's suppose that we are in R3. So ordered triples. And for A, well, first of all, how many vectors does a basis have for R3? You can type it or you can unmute and say it.
3.
3, okay? So this would have 3 basis vectors. If you want the easiest one, it'd be E1, E2, and E3. And let's suppose we have a set with 4 vectors. So we're actually going to take a set. -2, 6. So for A, what it says is if we have more than 3 vectors, that set has to be linearly dependent. And let's see why that happens. So I'm going to set up a linear combination of those. I'm going to take C1 times the first one, C2 times the second one, etc. And set it equal to 0. How many equations will I have in my system if I write that as a system of equations?
Three.
3 equations, yep. It'll be, the first column would be 1, 0, 4. Second one's going to be -1, 2, -3, 0, 4, 4, -2, 5, 6, and 0, 0, 0. So I've got 3 equations and 4 variables. Remember that this first column represents the first component. Sorry, the first row represents the first component. This is the second one, and this is the third one. So you've got 3 equations and 4 variables, which means that one of those variables is free, right? There's no way there's no way one of those 4 can be defined because we only have 3 equations. And if I have one free variable, that means one vector is a multiple of something else. I should say at least, because it could be more than one, but at least one vector is a multiple of another, which makes it linearly dependent. So if you have an extra vector, there's just too much there to work with. Something's going to be a multiple of another vector in the set. All right, let's do the same thing with B. But let's suppose we have less than 3 vectors. So I'm going to say S this time is, let's say it's 1, 0, 4, and -1, 2, -3. If I set up a linear combination of those, and I'm just going to set it equal to X, Y, and Z. Then C1 minus C2 is X. 2C2 is Y. 4C1 minus 3C2 is Z. What can you tell me about those expressions? At least one of those is a multiple of the other 2, correct? That's pretty easy to see here. So what you get is another same case, at least one vector is a multiple of another, we'll say.
So for a vector or a set to be linearly independent. It has, like, if it's an R3,
Yep.
the set has to have 3 vectors for us to test it.
Exactly, and you just said theorem 4.5.1.
Where
Okay. Well,
Yes, it has to have exactly the number of vectors that it's supposed to have.
those
Okay.
are
Okay, so
those
what
are
happens here
equations.
is you get at least one vector. All of these vectors are going to be multiples of another. And so you get, you can't get all of the vectors in R3. Hopefully everybody's done with that page. I'm going to go to the next one.
so like on the test, if you were to give us a set of 4 vectors, but it was an R3, could we just say straight up linearly dependent because of this?
Exactly. Yep.
Got it.
And we're going to do an example like that. Jared's way ahead of the game today. I'm
I'm
impressed.
confused by your explanation. There were only 2 vectors there, and they
Yep.
were clearly not multiples of each other. They're definitely traveling in different directions.
Correct. But if you set up a system, we're going to have 3 equations and 2 variables.
Which means that if you choose 2 of the 2 variables to set x and y to some value, then
Right.
z
So
will
that
already be
in
determined.
order to
You'll
get
have
that,
no more
that
variables.
third equation has to be a multiple of the other 2, correct? It has to be an extraneous equation,
Mhm.
which means that you've got you have a, I don't want to say variable. Hold on, and let me think a second. There's going to be a vector in R3 that you can't get because you only have 2 vectors to multiply and add together. There are going to be some components that you can't get.
There will be there'll be a row of zeros in the reduced row echelon
Correct.
form matrix.
Yes. Think about it a little bit. Okay, let's go to theorem 4.5.1, which Jared already said. So any basis for a specific vector space has to have exactly the same number. All right, the number of vectors in a basis is a pretty important number, so we actually give this a name. Call it the dimension. You either write it this way or that way as a notation. And special part of the definition is that the 0 vector space has dimension 0. All right, let's talk about just some examples of vector spaces. So Rn has dimension, I didn't put my dim in front of there. What's the dimension of Rn? We already talked about it, that's n. The dimension of polynomials with degree at least n, or I should say n or less. Remember this from Tuesday?
Is that n+1?
Yes, exactly. Good, Ethan. The dimension of m by n matrices. Think about the number of standard basis vectors that you would need for those. I think we did a 3 by 2 on Tuesday. A 1 would have to rotate through every row and column, so it will be m times n. Okay, another example. No response from anyone. Thought at least Jared would pipe up and say no. It's got to be linearly dependent, right? It's got 5 vectors.
Sorry, I was falling behind notes.
That's right. Okay, there have you got enough page that there you go.
Good.
So it's as simple as that. You should be able to look at, for example, for polynomials, if I give you a set of 5 polynomials for, let's say P7, it would have to have 8 vectors in order to be a vector space or be a basis for the vector space. So you could say that it doesn't span the space. There's a no from Sarah. Thank you. All right. Jed, what you need to do is click on that little go slower button. Do you have that? I think those are new. I don't remember those before this week.
Where are the go slower button?
Like when I click on the manage or the participants button at the bottom and you get the pane on the right that shows you who's in the class. Right below that, there's a little strip. There's a yes, no, go slower, go faster. You can clap. I think there's a cup of coffee. Need a break.
All right, yeah, I see it. Sorry.
That's right. So somebody said go faster. Okay, let's go on to our next example. I will scan these notes and put them, once in a while my phone doesn't want to focus. There we go. I will scan the notes and post them again, so if you get behind, you can always fill them in later. This gives us the solution to a homogeneous system. And obviously, this is linearly dependent. You have x1 as a multiple of all the other three variables. In other words, x2, x3, and x4 are all free variables. x1 is the only one that's a leading variable. And they want us to give a basis or find the dimension of the solution space. So all the solutions to the homogeneous system. In order to do that, we need to actually find out what those vectors are. So we need to find out how to write this solution as a linear combination of some vectors. I'm going to do this two ways. So the first one is if I take, sorry, that should be r, not 4. R times 1, nope, 4, 1, 0, 0. See if you can figure out where that comes from. R is times 4 here, 1 there, nothing there, nothing there. I'm going to take S times -3, 0, 1, 0. And I'm going to take T times 1, 0, 0, 1. And that gives you the same thing as what's underlined there. So now what I have is I have this solution written as a linear combination of 3 vectors. Now, later on in this chapter, we're going to write those as vertical matrices. And for some people, that's easier to understand. So I want to show you what that looks like. You can take that solution and write it in vertical form. Break it up into 3 vectors, 1 for each variable. So this is 4r, r, 0, 0, -3s, 0, s, 0, and t, 0, 0, t, and then factor out your variables. And you get 4 times r times 4, 1, 0, 0. You get s times -3, 0, 1, 0, and t times 1, 0, 0, 1. for some people, it's just easier to look at it that way. All right, our next theorem. This is actually a pretty easy one to understand. We're not going to prove this. This one's called the plus-minus theorem. It's kind of nice when they actually have a name, so you can refer to them to something besides a number. Okay, so we're just going to start with a set of vectors. Has to be non-empty in a vector space. The first part says, if there's a vector that's outside of that set and it's linearly independent, you can add it. So if I'm going to shorthand here, linearly independent. Okay, so very simply, if I have a set that's linearly independent, and there's a vector that's it's not in the span, so it's not a linear combination of the vectors in S, then I can add it to S. This just says to take S union V, so take S and add V to it, and it will still be linearly independent. Vector V is not, here's my V, is not a linear combination of the vectors that are in S, and so if I add it to S, I will still have a linearly independent set.
So if a set is initially linearly independent, is there anything you can do to change that set to make it linear dependent?
Yes. If I were to take the sum of those two and add it to that set, that would be linearly dependent because that third vector would be a linear combination of the other two. Like 1 times the first one plus 1 times the second one. Add that together and put it in the set, then you'd have a dependent set.
Okay. All right, that makes sense.
All right, the second part. How do you spell expressible? It's I-B-L-E? I don't know. This one starts with a linearly dependent set. So at least one vector in S can be written as a linear combination of the other vectors. This says I can throw that vector out, S minus V, and S will still span exactly the same space that it did. That's an M, even though it doesn't look like it. It's ABLE, Sarah? That's what I wondered.
No, it's I. She corrected herself. I also looked on.
Oh,
I also
okay.
typed it into Google and it came
Thank
out.
you.
And I came out.
All right, let's move on to the next theorem, and I'm going to do a proof of this one. We haven't done a proof in a long time. So this is theorem 4.5.4. All right, so we are starting with a vector space that we know is n-dimensional, which means a basis has to have exactly n vectors in it. Oops. And we've got three different proofs we have to do here. If it says S is a basis for V, if S spans V, or S is linearly independent. So we need to assume S is a basis and show that it is linearly independent and spans. We need to start with S spanning V and show it's a basis, and S being linearly independent and show that S is a basis. So we've got three different things we have to do here. So I'm going to start. This means is a subset of, S is a subset of V with n vectors. So our first step is to assume S is a basis and show it is linearly independent. Or spans V. Oh, I did it with the reverse order. That's all right. This one should be really simple.
If S is the basis for V, then by definition it is linearly independent and spans V.
Exactly. Perfect, Ethan. So that one's really easy. If S is a basis, by definition, it has to be linearly independent and span. Okay, the second one is we're going to assume that S spans V. And now we want to show that it's a basis. So in order to do that, a basis has to be, it has to span and it has to be linearly independent. So we're going to show S is linearly independent. Let's suppose it's not. Then there has to be some vector that can be written as a linear combination of the others. So what would you do with that vector? Throw it out, right? Theorem 4.5.3 that we just looked at says we can take S and subtract that vector and it'll still span V. But how many vectors? Yes, thank you, Ethan, take it out. Now how many vectors do I have in my set though?
You'll have n minus 1.
Yes, n minus 1 vectors. That would be third.
N minus 1, it won't span, right?
Say that again.
If it's n minus 1, it won't span.
It contradicts. It has to have n vectors, and I think that's their. Oh no, that's 5.2. So if you go back to the very first theorem we looked at, if it has less than n vectors, then it doesn't span, which contradicts. We have to have n vectors in order to span.
Which
Therefore-
contradicts another. Essentially, we've simultaneously demonstrated that does and does not span V, which
Correct.
is a contradiction.
Yeah.
So our assumption
Yeah.
is false.
So S must be linearly independent. All right, one more. This one we're going to assume S is linearly independent. Oops, I forgot S. So what we have to show is that it spans V. And we're going to take the same approach that we did before. Let's suppose S doesn't span V. then there has to be a vector, we'll say v sub I, in S, not in the span.
You mean in V?
In S. There must be some vector that's, hold on. Oh, yes, in V, sorry. Thank you. So we can add that vector to S. And S will still be linearly independent from the same theorem that we just looked at. This is the plus minus theorem. How many vectors do we have in S now? It would be linearly independent. It just has too many vectors now, Ethan. It's not in the span of S, right? There's a vector in V that's not in S, not in the span of S. So if we can add that and we still have a linearly independent set, but now it has too many vectors. I'm not going to write out the conclusion. That's a full page proof already. All right. One last theorem here. I'm going to write out.
Said she's having sound issues.
Who is? Sarah is. Anybody else having sound issues?
You should probably ask that in the chat, because anyone who's having sound issues can't hear you ask that.
True. I'll type it. Okay. All right, let me write out this last proof or theorem. Oops, I left out, let S be A. Sorry. This is finite set of vectors. Okay, so what this says is if you have a set of vectors, this is a finite set of vectors, where it's not saying how many are in it, but if you have a finite set of vectors in a finite dimensional vector space V, if you have a set that spans, but it's not a basis, that means it spans, so you can get everything in the vector space, but it's not linearly independent, is basically what it's saying. Then you can take out the appropriate vectors and end up with a basis. And then this one is the opposite. If we've got a linearly independent set, but it doesn't span, then you can add things to it. All right, this isn't really relative to that theorem, but I want to do one last little example.
I would say no.
Because why?
Just
How
do
many-
the last part of the, maybe Ethan says.
Oh, this
yeah.
has nothing to do with the last theorem. I'm just throwing one last example in here. So don't pay any attention to the theorem we just did. How many vectors do you need in for R2 for a basis?
2.
You know, it has to be 2, correct? I don't like the way that looks. And which is what we have. Now we need to look to see if they're independent. Is either one of those a multiple of the other? Okay, Ethan says no. Okay, so yes. Neither one is a multiple. And the theorem that we spent so long working on, theorem 4.5.4, I'm going to go back to that one. I'm going to summarize that just a little bit. Can find it. This one, this gives us a lot of freedom because it says if you know you have n vectors in a set, all you have to know is it's either linearly independent or it spans, and you know it's a basis. So you only need to know one of those things now, and then you know that it's a basis. So it has to have the correct number and either be linearly independent or span. Let me write that out.
So in R1, would that make all, if it, any single component in R1 make it a basis?
So you only need one vector, just a real number, basically.
Yeah, that's what I was making sure.
Pretty boring. Okay, there's one theorem that I didn't make it to, this one. So I will do that one at the very beginning of class on Tuesday. We'll do that one. I do want you to go to, I'm going to share a screen with you here. In Blackboard, I've added a new folder here under content. So under course content, there's an examples folder. And I added 2 examples in there. And these are examples that you might want. They're like, this one's actually from the homework. This one's very similar to one from the homework. And I don't have time to work through those, but you can look through those and those will apply to what your homework looks like. So I would suggest that you go look at those. Right now, if you look at the calendar, I have your next quiz scheduled for the 21st that day. We'll see how things go between now and then, but I'm planning on a quiz that day over 4.4 to 4.6. So we have to do 4.6 yet before we can take that quiz.